Hello and welcome back to Probabilus. Today is a wonderful Wednesday evening, so that means we will be talking about calculus. So let's just get into the content, figure out what we're learning about today. Today we are discussing applications of derivatives. So in the last calculus lesson, we learned about derivatives. We learned what they are, slope of the tangent line of a function. They can also demonstrate rates of change. In fact, we saw some applications of like water filling a tank, and we used derivatives to see the rate of water filling it and seeing the height of the water. So today we're going to see more applications. And all of those tips and tricks and things we've learned, techniques that we use for derivatives, the chain rule, product rule, power rule, all of those are going to be very helpful because we're just going to be doing a ton of derivatives from here on out. So, specifically, we will be focusing on one particular application, which is Extrema. So, Extrema, very cool word in my opinion. I really like to say it. Let's figure out what are extrema. So, as always, we'll do some definitions. So, we define a function f, well, rather, f is defined, and it's defined on an interval, which we'll denote with I, and it contains c, so c is some point within the interval. And then we say that f of c, so the function evaluated at that point c, which we chose, it's called the minimum of f, the minimum of the function f on the interval I, when f of c, the function evaluated at c, is less than or equal to f of x for all x in I. So that means if every single point within the interval, the infinite amount of points within that interval, if we evaluate the function on each of those points, then we have the point such that the function evaluated is the smallest out of all of the points, that is called the minimum. That's what it's saying here. Similarly, f of c is the maximum of the function f on the interval when f of c is greater than or equal to f of x for all x in I. So again, if we were to compute the function value for all infinite amount of points in the interval I, we denote some point c to be the maximum when the function evaluated at that point is the highest value out of all of the other values in the interval. So these are pretty basic words. We've seen minimum and maximum in past math classes. And they are basically what you imagine them to be. Now we've just defined them mathematically. Okay. And the minimum and maximum values of a function on an interval are the extrema of the function. So when we say extrema, we're talking about minima, maxima of a function. It's just a fancy word we use to encompass both of those. Additionally, the minimum and maximum are called the absolute maximum minimum and the global maximum and minimum. So that's kind of weird. Like, why would we add different terms that especially mean the same thing, absolute and global, just to describe what a minimum and maximum are? The thing is, we can have different types of maxima and minima, and we'll see that shortly. But when we see absolute and global maximum minimum, we're talking about like the highest value of the function or the lowest value of the function. And lastly, very, very important, it may seem kind of obvious, but it's extremely important. In an interval, the extrema can occur within the interval or at the endpoints. This final clause is super important. It's very possible for the extrema to be at the endpoints of our interval. And when we calculate extrema, it's super easy to forget that, that we have to test the intervals. So I will be reminding us of it many times, that we have to test our endpoints. So yeah, that is just a good signal right now that we should be aware of it. So now we have a nice little visual representation of what's going on. So we have some function here, and we have an interval from a to b. So the function is defined on this interval because, well, we see a picture of it. So within this interval, this point at C3 is the absolute minimum because for all other points within A and B, the function evaluated at those points are all greater than or equal to the function evaluated at C3. It's the lowest point. The absolute maximum is this point at B. So right now we're at an endpoint. We're at B, and we can see that the function evaluated at B is greater than or equal to the function evaluated at all other points in the interval. So that's saying that if we take this line here, which is where f of b is evaluated at, we can see that the rest of the function lies below it. So it's an absolute maximum. Similarly, if we were to do that for the minimum, everything lies above it. So like this point at C2, if we were to draw that line, it's not an absolute maximum because the entire function does not lie below it. And it's not an absolute minimum either because the entire function doesn't lie above it. However, these points are highlighted because they are somewhat special, and we'll see that in just a moment. But first, we have to introduce something called the extreme value theorem. So this says, if f is continuous on a closed interval from a to b, then f has both a minimum and a maximum on the interval. So this means we have, let me just draw it out. So we have like our axes here, and let's just define like the section within red to be our interval that we're looking at. We can take any sort of function we want. Let me redraw that. Something like this. And if we look within the interval, I'll just make these lines a little bit bigger, there will be a minimum or maximum within it, which seems pretty obvious. And it's saying within the interval. So in this case, the maximum occurs at like this point up here. And even though that's not the maximum of the function, because there's like a point up here on the right of the function that's like more maximal than the red point, the red point is the maximum within the interval. And similarly, something like this would be the minimum within that interval. So this seems like a pretty simple theorem, and it kind of is. But this is what we call an existence theorem. It tells us whether a minimum and maximum exists, but it doesn't tell us where these extrema are, what the values of the extrema are. It just tells us there are these extrema within an interval. So yeah, that's that. So now we talk about relative extrema. So this is where we introduce another adjective. You know, we had global maximum, absolute maximum, stuff like that. Now we have relative maxima, relative minima. So let's take a look at the definitions. So now we consider an open interval containing some point c on which f of c is the maximum. So that's just saying c is the maximum, right? The function evaluated at c is maximum. Fine. Then f of c is called a relative maximum of f, or we can say that f has a relative maximum at c comma f of c. So this is saying that like if within an interval we have a maximum, that's called a relative maximum. So we're looking within an interval here. So if we go back to this example here, the red dot, like here, that is called a relative maximum, which is a better descriptive term of it, because if we just called this the maximum, I mean, yeah, it's the maximum within the interval, but it's not the maximum of the function because that occurs somewhere up here, maybe. So this is the relative maximum within the interval. And similarly, this is the relative minimum. And this is the relative maximum of a lot of different intervals. For example, I could make, you know, a new interval. So we're now considering like this space here. And this is still the relative maximum of it. So yeah, that is that. And similarly, relative minimum is basically what we expect it to be. It's the minimum on the interval. We call that a relative minimum. So I wrote here that a relative maximum is like a hill and a relative minimum is like a valley. So if we go back to this example here, this is sort of like a hill. That's where the maximum occurs. And this is like a valley. The minimum is at the bottom of the valley. So that's a nice way of remembering it. So here we have a better description of what's going on with a picture. So we have this function, and at this endpoint here, at the top left, that's a global maximum because there's no other points on the function such that the function evaluated at like that x value has a value greater than the function value at this global maximum, right? And we can do the little trick that I showed that if you draw this line here, the entire function lies below it. Similarly, down here, we're in a valley. This is a global minimum. And you can use the mathematical definition, or we can use this brief visual description where if I draw that line, the entire function lies above it. So it's a global minimum. This is like, it kind of looks like the top of a hill, right? That looks like a hill. This is the top of it. This seems like it's important. It's some sort of maximum. And indeed, it's a local maximum. It's not a global maximum because when I draw this line, the entire function is not below it. The left part of it, some of it is still above it. So like if we were to consider an interval, perhaps like from here to here, right? This would be the maximum within that interval. So that's what we call a local maximum. And for very similar reasons, we have a local minimum at this point here. This is like a valley, we're coming down this valley, and it's the bottom point of the valley. And again, if we were to draw the line here, the entire function does not lie solely above it, so we can't call it a global minimum. So visually, these maxima and minima are pretty easy to detect, especially the global maximum and global minimum, because we just look for the most extreme points, the highest values and the lowest values. But also these local extrema are also kind of easy to visualize because they're sort of like where the function changes direction, right? Here we're going upwards, and then we reach this point here, which is at like this peak of a hill, and then we start going downwards. And similarly for the local minimum, we're going downwards, and then we hit this point here, and then we start going upwards. So we can start to think about how extrema may tell us how the function changes direction. And if we're aware of what functions and like what direction has to do with functions, maybe you're starting to think about, this could have something to do with a tangent line, because tangent kind of tells us the direction of the function. And you would be absolutely correct. That is why we are in the section of applications of derivatives. We will be using derivatives to calculate the extrema. But before we get into that, we have to introduce this new term, which is quite critical, pun intended, which we call a critical number. So yeah, this word is thrown around a lot in calculus, so it's helpful to know what it is. So we have a function, it's defined at c. If the first derivative of the function evaluated at c is equal to 0, or f is not differentiable at c, so that means this just means that f prime of c does not exist. That's saying the same thing. Then c is a critical number of f. So a quick way to see if a value is a critical number of the function, take the first derivative of the function, plug in that value. If you get 0 or dne, then it's a critical number. And here we see it graphically. This point here, the first derivative does not exist because we have a corner. So since f prime of c is dne, then that is called a critical point. For this parabolic graph here, at this peak, f prime of c equals 0. This is actually the tangent line, and you can see that the slope is 0. So since it's 0, that is also a critical point. And if f has a relative minimum or a relative maximum at x equals c, then c is the critical number of f. Interesting. So let's just scroll back a little bit. This says that, okay, if we have this minimum here, then that minimum is a critical value, or a critical point, I may say. Like, those terms are used interchangeably, critical value or critical point. So this is saying if we have a critical point, or if we have a minimum here, then it's also a critical point. And by definition, that tells us that the first derivative at this point is either 0 or does not exist. And if we take a look at the tangent line here, it is actually horizontal, which means that the derivative evaluated there is 0 because the slope of that line is 0. So I think that's actually really cool. We know what the first derivative evaluated at a global maximum, or just a maximum or minimum, is. So yeah, very helpful definition. So now I've provided a step-by-step process to find extrema on a closed interval. So how do we do this? Suppose we have this function and we have an interval. Those are given to us. And we want to find all the critical values. Well, we start out by finding the critical values of the function in a comma b, which is the open interval. And we'll worry about why it's open in just a moment. And to do this, we find the critical values by taking the first derivative and seeing where it's equal to 0 or does not exist, just by the definition of a critical value. Then, once we get those critical values, we can evaluate f at each of those critical values. Additionally, now we consider the closed interval a comma b, and we evaluate f at the endpoints of a and b. So this is just saying do f of a and f of b. Then, once we've evaluated f at all of these points, the greatest evaluation value is the maximum, and the smallest is the minimum. So why exactly does this work? It works because we know that all critical values are either we know that the extrema are critical values of the function. So why don't we just start by finding all critical values, right? Because certainly the maximum or minimum will be included within that set of critical values. So once we find those critical values, we just need to figure out which of those, when evaluated on the function, is the highest or the lowest to classify which is the maximum or the minimum. So we do that, that's step 2. But then we also have to take care of the endpoints. Remember, one of the first slides, I said don't forget about the endpoints. So that's why we do that here. And then we have a ton of these f of a's, f of b, f of whatever. And then we can figure out, f of critical value 3 is the highest out of all of them, so that's the maximum, something like that. So we'll do that with an example here. So we are tasked to find the extrema of f of x equals 3x to the 4th minus 4x cubed on the closed interval -1, 2. So let's just follow the steps that I provided. Step 1, we're going to find the critical values. And how do we do that? We evaluate f prime and see where it equals 0 or dne. So let's do that. We have f of x equals 3x to the 4th minus 4x cubed. So this tells us f prime of x equals 12x cubed minus 12x squared. So that's just using the power rule. And then let's just factor it out a little bit. Just to keep it nice, we can factor out a 12x squared term from both of these, and we get something like this. So we want to see where it equals 0 or dne. Let's just start with dne. Is there any point x in which this function, when evaluated, it doesn't exist? The answer is no. And usually we would expect the function to not exist at a point if perhaps we had a fraction and like the denominator became 0, right? When we divide by 0, it's undefined, it doesn't exist. In this case, we're just multiplying numbers. No matter what value of x I choose, it'll always exist. So there's nothing that makes it dne. What about 0? that might be a little trickier. So let's just set f prime equal to 0. F prime of x equals this, equals 0, right? So we can see here that either 12x squared must be 0 and or x minus 1 must be 0, right? These were just multiplying things that depend on x, and the only way for the product to equal 0 is if one of the terms is equal to 0. So this tells us that x equals 0, 1 are critical values. Critical values. Because when you plug in f prime of 0, you'll get 0. And if you plug in f prime of 1, you'll also get 0. So now I'm going to combine steps 2 and 3. 2 and 3. This is saying evaluate f at critical points. I'll just use some abbreviations, and the endpoints, right? We can't forget about the endpoints. So what we can do is we can create like a nice little table here. So on the left will be the x value, and on the right will be f of that x value. So what are the points we have to test? We have to test first, let's just do the critical values. So x equals 0, x equals 1, and then the interval has -1 and 2 as endpoints. So let's just evaluate those. Let me just zoom in here, and I'll just write the original function here so it's easily accessible. So this is saying, let's compute f of 0, which is equal to 3 times 0 to the 4th minus 4 times 0 cubed, and that just equals 0. Okay, so that's pretty simple. Now for this one, we do f of 1. This is equal to 3 times 1 to the 4th minus 4 times 1 cubed. That equals -1. Okay, so now we can already see that at x equals 0, that is not a minimum, because there exists another point within the interval such that f of that point is less than f of 0, right? F of 0 is 0, f of 1 is -1, so there's no way this can be a minimum. It's possible that 1 could be a minimum, but we have to first finish computing the endpoints. So let's do f of -1, that equals 3 times -1 to the 4th minus 4 times -1 cubed. This equals 7. And lastly, we'll do f of 2, 3 times 2 to the 4th minus 4 times 2 cubed. This gives us 16. So when we look at this chart, we just look for the lowest value and the highest value. So the lowest value is -1, so this tells us this is a minimum. And the highest value is 16, which tells us that that is a maximum. So that basically concludes the problem, but I always like to write just out in words, so that way whoever is viewing my solution knows exactly what I'm doing. We can say there is a minimum at x equals 1, and it's x equals 1 because even though we labeled this -1 as the minimum, this is the function value at x equals 1. And then similarly, there is a maximum at x equals 2, right? And that comes from the bottom row. And if we wanted to be really special, we could just say that like what those coordinates are. So this would be 1, -1. This would be 2, 7, or sorry, 2, 16. But yeah, that is finding the minima and maximum of a function on an interval. So it's just a very step-by-step process. I realized I didn't do step 4, but I didn't label it. I'll just do that here, just so that way we can see it visually. But yeah, that's basically it. So let's do some more practice with a different function. So now I won't write out the steps. Hopefully we're familiar with them. But like the first step is to find the critical values. And to do that, we need f prime of x. So f prime of x equals derivative of 2x is 2 minus derivative of 3x to the 2/3 is 2x to the negative 1/3, I believe. Just some sort of power rule right there. So I'm going to rewrite this as 2 minus 2 over x to the 1/3 because I am not a fan of, negative exponents. And, well, I know that I want to evaluate it to see where it's, does not exist. So I'm just going to create one total fraction, which means I'm going to common denominatorize the first term. So let's just say that this is equal to 2x to the 1/3 over x to the 1/3 minus 2 over x to the 1/3, right? Because now we can subtract these two fractions, and we're left with 2x to the 1/3 minus 2 all over x to the 1/3, and since I'm feeling up for it, let's just factor out the 2, right? So where is f prime of x equal to dne? F prime of x equals dne when the denominator equals 0, right? Because we can't divide by 0. So this tells us when x to the 1/3 equals 0, which is when x equals 0. So if we do f prime of 0, we should get dne. You can try it for yourself. What about when f prime of x equals 0? This occurs when the numerator equals 0. 0 divided by anything, except for 0, is 0. And we don't need to worry about 0 divided by 0 because kind of already took care of that with the denominator. But, okay, let's see. When is the numerator 0? That's when 2 times this quantity equals 0. And that tells us that x to the 1/3 minus 1 equals 0, which tells us x to the 1/3 equals 1. And that tells us x equals 1 cubed, which is 1. So our critical values are x equals 0 and x equals 1. Cool. So now we can create our chart and do the same thing we did before. So we'll do the x value on the left side. We'll do f of x, which is equal to 2x minus 3x to the 2/3 on the right side. And what are the values we have to test? Well, we have to test the critical values we just found, 0 and 1. And then we also have to do the endpoints, which are -1 and 3. So let's do it. F of 0 equals 2 times 0 minus 3 times 0 to the 2/3. That's equal to 0. 0 to any power is 0. Except 0. Things get funky with 0, I'm sorry. But yeah, that's just equal to 0. F of 1, 2 times 1 minus 3 times 1 to the 2/3. 1 to any power is 1. Feeling pretty confident about that. So this is equal to 2 minus 3 equals -1. Okay? Now we do f of -1. That's equal to 2 times -1 minus 3 times -1 to the 2/3. Okay, now we have to figure out. So the first term is -2, and then we subtract 3 times -1 to the 2/3. So the way we compute fractional powers is, I'll just do a brief tangent over here. If we have k to the x divided by y, this is equal to the yth root of k to the x, right? So this is saying if we have 8 to the 2/3, this is equal to the cube root of 8 squared, right? So we can go here, and we have the 2/3 power, so this is the cube root of -1 squared. So that's equal to -2 minus 3. The cube root of -1 squared, well, -1 squared is 1, so the cube root of 1 is 1. So this is 3 times 1. So this is equal to negative 5. And then finally we have to do f of 3. So this is equal to 2 times 3 minus 3 times negative, nope, not negative 1, we're at 3 now, to the 2/3. So this is equal to 6 minus 3 times the cube root of 3 squared. So that's 6 minus 3 times the cube root of 9. And I'm not really sure what the cube root of 9 is. But we can always use a calculator for it, which in fact I suggest you to do. And we should get around negative 0.24. So now we have our values, and we can classify them as maxima or minima. So we have 0, negative 1, negative 5, and negative 0.24. So somehow 0 is our maximum, because all of the other values are less than it. And negative 5 is our minimum. And as always, I would like to add a sentence here, just saying what we found. So notice that the max occurs at x equals 0, and the min occurs at x equals negative 1. So let's just write out, there is a minimum at x equals negative 1, and there is a maximum at x equals 0. So that's another problem down, very similar to the previous one, but it's good to do problems with some similarities between them so we can be confident when we come across them. So now, again, it's a similar thing. We're finding the extrema, but now we have some trigonometric functions to deal with. And once again, we're given an interval, 0 to 2 pi, so the process is very similar. It's just that computing the derivative will be a little bit annoying, if you will. So let's compute f prime of x. Derivative of 2 sine x equals 2 cosine x minus cosine of 2x. We need the derivative of that. That is a chain rule problem. So the derivative of the outside, derivative of cosine of some quantity, is negative sine of that quantity. So this will be negative sine of the quantity, which is 2x. And then we have to take the derivative of the inside of the function. So the derivative of 2x is 2. So putting this all together, we get 2 cosine of x plus 2 sine 2x. And now we ask, where does f prime of x equal dne? And this is nowhere, because sine and cosine are, they're defined everywhere. No matter what you plug into sine or cosine, you will always get a result, right? Because radians, the way that radians are developed, if you think about the unit circle, you just keep on going round and around, no matter how many radians you want. Same thing with degrees, if we were working with degrees, but we're not, because we're evaluated 0 to 2 pi, that's our interval. But even if I wanted, I could find sine of 10 billion degrees if I wanted to. I don't want to, but the point is that sine and cosine are never undefined. What about f prime of x equals 0? Where does that occur? Well, let's just figure it out. We want 2 cosine of x plus 2 sine 2x to equal 0. And this seems a little bit complex, but if we recall sine of 2x, there's a nice little formula that tells us that it's 2 sine x cosine x. That's an equivalent form. So this is telling us now we want 2 cosine of x plus 2 times 2 sine x cosine x. That should equal 0. So let's just distribute the 2n. We get 4 sine x cosine x equals 0. And now we can factor out a 2 cosine x term. 2 cosine of x times 1 plus 2 sine x equals 0. So either cosine of x is 0, or 1 plus 2 sine of x equals 0. So let me just write that out. Either cosine x equals 0, or 1 plus sine, 2 sine x. 0. Okay, so we have two cases. Let's just figure out what values of x make it equal to 0. So this occurs, this first case occurs when x equals pi over 2 or 3 pi over 2. Really any odd number times pi over 2, but we don't include 5 pi over 2, 7 pi over 2, or even negative pi over 2, because we're on the interval 0 to 2 pi. So we only want values within that interval. So now let's figure out when 1 plus 2 sine x equals 0. So this is when 2 sine x equals negative 1, or sine of x equals negative 1/2. And this occurs when x equals 7 pi over 6, or 11 pi over 6. So now we have 4 critical values: pi over 2, 3 pi over 2, 7 pi over 6, 11 pi over 6. So it's more than what we saw previously, but we do the same thing as we did before. We'll create a nice little chart where this is our x value, and then we want f of x, so the function evaluated at that point. So this is 2 sine x minus cosine of 2x, right? And so let me just list the critical values that we have. We have pi over 2, 3 pi over 2, 7 pi over 6, 11 pi over 6. And then lastly, we have to account for our endpoints, which is 0 and 2 pi. And now, what some people think is the best part about all of this, or as some people think it's the worst part about all of this, is doing the algebra. We do have to be careful here that we don't make mistakes, so it can be tedious, but sometimes it's fun. I kind of enjoy it. F of pi over 2 equals 2 sine of pi over 2 minus cosine of 2 times pi over 2, so that's just pi, right? This is equal to sine, oh gosh, I have to recall all of my sines and cosines, which I've definitely forgotten. Sine of pi over 2 is 1, so this is 2 minus cosine of pi is negative 1, so that equals 3. Now we do 3 pi over 2. Hopefully I don't make any mistakes. 2 sine of 3 pi over 2 minus cosine of 3 pi over 2 times 2, so this is 3 pi. That is equal to, well, sine of 3 pi over 2, I believe that is negative 1. So 2 times negative 1 is negative 2, minus cosine of 3 pi is equal to cosine of pi, which is negative 1. So I believe this is equal to negative 1. F of 7 pi over 6. Wow, this is challenging. 2 sine 7 pi over 6 minus cosine. 7 pi over 6 times 2 is 7 pi over 3. This is equal to, oh goodness. Well, I don't feel like computing it out, but the answer is negative 3 over 2. Just going to save us a little bit of time here. 11 pi over 6. I'll just write out the formula, so that way you can check to make sure you're doing it correctly. 11 pi over 3. This should be equal to negative 3 over 2. And lastly, we do our endpoints. 2 sine of 0 minus cosine of 0, which this one I can handle. That's equal to negative 1. And then f of 2 pi, 2 sine of 2 pi minus cosine of 4 pi, which is also equal to negative 1. So now we look at all of our values and we're like, okay, which one is the largest, which one's the smallest? And it's pretty easy to see that 3 is the largest, so that's a maximum. Now the smallest, well, we have 3 negative 1s and we have 2 negative 3 halves. Negative 3 halves is smaller than negative 1, so that means that's the minimum. But which one of these two is the minimum? Well, they're both minimums. Because if you think back to our definition of minimum, here, when the function evaluated at that point is less than or equal to all other f of x. So it's fine if it's equal. We can just have another minimum. It's perfectly fine. So I'll scroll back here. So this is a minimum. This is a minimum. And then we can just write a concluding statement at the bottom. There are minima when x equals 7 pi over 6 and x equals 11 pi over 6. And there's a maximum when x equals pi over 2. Right? So that is that. Just multiple minima. We can have multiple maxima as well. But yeah, that's a quick example right there. So that concludes the first section, introducing extrema. Now we have to learn some theorems, Rolle's theorem and the mean value theorem, which are very important. But before we get into that, I'm going to take a quick sip of water because I've been talking for 40 minutes. Already running low on water. Okay, so let's take a look at these theorems. Like I said, they're important, but they're also really cool. So Rolle's theorem is first. F is a continuous function on a closed interval a to b, and it's differentiable on the open interval a to b. And what it's saying is if the endpoints, when evaluated on the function, are the same, then there exists some value within that interval such that the derivative evaluated at that point is 0. I'm experiencing a little bit of technical difficulty, so I'm going to take care of that, and we'll be back in just a moment. Okay, we're back. So we have an interval, and the function evaluated at the endpoint is the same. So there exists some point such that the derivative at that point is 0. And for some, this might be intuitive. For others, this might not be. I know for me, I was like, wait, that I should have thought about that sooner. And it makes a lot of sense. And I'll do a little sketch about it, and then we'll analyze the picture they provided. But let's just say I have these axes here. And this is one part of my interval, and that's the other part of my interval. And I want the function evaluated at those points to be the same, so let's just say it's equal to 0. No matter what differentiable function I draw, it is impossible for me to have no point such that the derivative is equal to 0. Like, I can do something super weird, something like that, and in fact, I didn't even come close to proving it's not true because there's so many places where the first derivative is 0. Remember, the minima and maxima are critical points, and so that means their first derivative is equal to 0 or dne, so we can just take a look at the relative and global extrema. So let's take a look at this one right here, and we can see that the tangent line is horizontal, so the derivative there is 0. And same with here, and same with here, and same with here, and same with here. So that didn't work. What if I just like do one single jump like that, then again, there's still a maxima in this case. There could be a minima, but at that point, the tangent line has slope 0. Even if I do a constant function, that's actually the worst case because now all of the points within that interval have f prime equal to 0. So no matter what you try, there will always be some point that's equal to 0, its first derivative. And that is Rolle's theorem. So I think that's pretty cool. Now we'll look at the mean value theorem, which still boggles my mind to this day, but it makes sense. So now we have a function closed interval like we're used to. It's differentiable, and now we're saying that if those things are true, then we have some value in the interval such that the first derivative at that point is equal to the function evaluated at b minus the function evaluated at a, divided by the difference of the x values of those two endpoints. And this equation should look very familiar because that's the slope of the line connecting those 2 points. You take the function evaluated at those points and you subtract them and divide it by the difference in their x coordinates. So that is drawing this line between a and b and finding the slope of it. And what they're saying is no matter what function we draw connecting a and b, so long as it's differentiable in that open interval, there will always be a point such that the derivative at that point is equal to the slope of the line connecting those 2 points. And I don't really have a better way of describing it than just by what we see in the visual. We have this black function drawn, and we see that there's multiple points actually where the slope is the same. So this is just mind-blowing how that's even true. But it is true. It's called the mean value theorem, and it's quite important. Okay. So now we're going to introduce something called increasing and decreasing functions. Well, maybe not introduce that, but maybe the first derivative test is something that's new. So this helps us classify minima and maxima even more. So now we can determine local minima, local maxima, stuff like that. So this will give us a new technique. So we've learned how to detect critical points, which is amazing. Now we have to learn how to classify them, right? So like we did a little bit of that where we found the critical points, and sometimes they were the minimum of the function, sometimes they were the maximum of the function, but other times they weren't. So we need to figure out like what's going on there. So we say that a function is increasing on an interval when if we take any two numbers, x1 and x2, in the interval, where x1 is less than x2, then the function evaluated at x1 is less than the function evaluated at x2. So, and then decreasing is the same thing, where we take x1, x2, such that x1 is less than x2, but now the function evaluated at x1 is greater than the function evaluated at x2. So let's just take a look at an example. So we have our axes here, and we have some function like this. And we'll consider the interval from basically the part of the x-axis that I drew. This function, well, by the looks of it, it's increasing. And it is. Take any two x points, let's just do something here and here, where x1 is less than x2, then the function evaluated at x1 should be less than the function evaluated at x2, and that is true. And we can see that there. Let's take a look at another example. Something like, nah, that's not quite what I wanted to do. Something like this. Let me do it in red. Right? So this, by the looks of it, it's decreasing. Let me just specify the interval as well. It looks like it's decreasing, because as we go right, it's going down. And it is. Once again, let's just take any two x points. I'll just say that's x1. We'll say this is x2 because x1 needs to be less than x2. And if we take the function evaluated at x1 and the function evaluated at x2, we see that f of x1 is greater than f of x2. And it's not that we just found 2 points such that it's true. It must be true for every pair of points. And let's just take a look at one more example. So same interval. Now we have something like this. And now, well, let's see. Let's just say this is my x1 and this is my x2. Then the function evaluated at f1 is greater than the function evaluated at f2, which makes us think that, okay, by definition, this function must be decreasing. But that's not true for all x1 and x2. For example, let's just get rid of the original x1. Oh no, I got rid of my axis. That's not correct. Something like that. And let's make what we just drew, let's call that x1, and introduce a new point, not there, here, which is x2. So now the function evaluated at x1 is less than the function evaluated at x2. So that would tell us that it's increasing. But we just said it was decreasing. And so a function can't be both increasing and decreasing. Well, actually it can be, but we can't strictly call that function either increasing or decreasing on the interval. And this should be pretty self-explanatory because by the looks of it, it's not. But let's just say that I alter my interval. So let's consider the orange interval first. In that interval, the function is decreasing, right? You can just take any 2 points and you'll see that it's true. F of x1 is greater than f of x2. Now we consider the green interval, and we can see that in that side it's increasing. F of x1 is less than f of x2. So those are just a couple of examples there. Yeah, it's pretty simple when we see the graphs, but when we're not supplied with the graphs, we need a way of defining it mathematically. So we can actually detect increasing and decreasing parts of the function using the first derivative. So we see this function f here, and we have these intervals. First we have from x equals 0 to x equals a, so from here to here. And so we're looking at this part of the function. And if you were to take the first derivative at any point, it would be less than 0. So let's just take a random point, consider the tangent line. The slope of that tangent line is negative. Similarly, let's take another point here. The slope of that tangent line is also negative. All of these tangent lines have negative slope. So if the first derivative is less than 0, the function is decreasing. Now let's consider a new interval. So this is from x equals a to x equals b. Now if we take the tangent line at any point, it's always the same tangent line because we're on a constant function there. So that means the first derivative is equal to 0 because it's constant. So if that's the case, then it's neither increasing nor decreasing. It's just constant. Finally, if we consider the interval from x equals b to just some point here, now we can see if we take the first derivative at any point, the tangent line, the slope of the tangent line is always positive. So f prime of x is greater than 0. If we get that condition, then we can say that the function is increasing. So just like that, just by taking the first derivative, we can tell what the function is doing. So now we'll describe a test for increasing and decreasing function. This is basically what I just said, except now put in better mathematical terms. So f is a function continuous on a closed interval, differentiable on the open interval. If f prime of x is greater than 0 for all x in the interval, then f is increasing. So that's this here. F prime of x is greater than 0, and it's increasing. If it's less than 0, then it's decreasing. So that's this left part here, decreasing. And if it's 0, then it's constant. So basically what I just said. Okay, so now we are tasked with finding the open intervals on which f of x equals that is increasing or decreasing. So, how do we do this? Well, I'm not really sure. I'm joking, obviously. But the thing to note is that if the first derivative is less than 0 or greater than 0, then it's not equal to 0, which sounds so dumb. Like, obviously, right? If it's less than 0, it's not equal to 0. But that's really critical. And once again, this time the pun was actually unintended. But if we know that the first derivative at some point is 0, then we know that point is a critical point. So, within the increasing part of a function, there are no critical points. However, a critical point can mark the change of whether or not a function is increasing or decreasing. So let me just sketch that out visually here. Let's just consider the parabola example that I did. Did I keep that drawing? Yeah, I did, here. Okay, so let's take a look at this. We said from here to here, from x equals like -5 to 0, just this -5 is chosen arbitrarily, in that interval the function is decreasing. But when we said the interval x equals 0 to x equals 5 or whatever, there it's increasing. So when x equals 0, that marks the change of when the function it's changing from decreasing to increasing. And what's special about that? Well, by the looks of it, at x equals 0, we have a minimum there. The tangent line is 0. The first derivative is 0. So what we can do is we can find the critical points of our function, and then we can test to like the left and right side of it to see where, like, if the function is increasing or decreasing before we hit that critical value. So let's do that. I don't want to use red. Getting tired of it. Let's do blue. Step 1. Find critical points. How do we do that? F prime of x equals dne, or f prime of x equals 0. So if f of x equals that, f prime of x equals 3x squared minus 3x. We can factor out a 3x term, we get x minus 1. There's no points where f prime of x equals dne. However, f prime of x equals 0 when 3x times x minus 1 equals 0. So this tells us that either x equals 0 or x minus 1 equals 0, which tells us that x equals 1. So these are our critical points. X equals 0, x equals 1. Okay. So notice how we don't have an interval, right? In the previous questions, they were like, find the extrema on this interval. Here, we don't have it. The function is not defined everywhere, from negative infinity to positive infinity. So we have to consider all of the intervals. So as always, we're going to create a chart. I really think charts are very helpful with extrema problems. So first, we're going to consider our intervals. Our first interval, starting from the left, goes from negative infinity to our first critical value at x equals 0. Because either the function is increasing or decreasing, there's no points in that interval such that the first derivative is 0, because we found the points where the first derivative is 0. Then we go from 0 to either the next critical point or to infinity. And in this case, we go to the next critical point, which is 1. And then finally, we go from 1 to infinity. So those are our intervals that we've broken the function into. Now, we have a test value. So this is what I was describing. we found the critical points. Now we have to determine to the left and right of the function, like, is the function increasing or decreasing? So a better way of putting that is now we've encapsulated these intervals. Let's just take a random value within that interval and see if the function is increasing or decreasing there. So, well, how do we do that? We evaluate the sign of f prime of x. Meaning, if the sign of f prime of x is negative, then the function is decreasing on that interval. And if it's positive, then it's increasing on that interval. So I'll just add another column for our conclusion. So let's just walk through it. Consider the interval negative infinity to 0. We just need a test value within it. So it could be anything. I like to stay away from the endpoints because just because it's a little funky that's where we're breaking up the interval. So we can just choose any points. I'm just going to choose x equals -1. It's small, easy to do algebra with. F prime of -1. That is equal to, I'm going to use this right here. This is equal to 3 times -1 times -1 minus 1, which is equal to 6, right? And 6 is greater than 0. So our conclusion is that it is increasing on this interval, right? So that takes care of the first interval. So now we'll do the second interval, 0 to 1, and we do the same thing. We choose a value, x equals 1/2 this time, because why not? F prime of 1/2. That equals 3 times 1/2 times 1/2 minus 1. This is equal to -3/4, I believe. And we can see that -3/4 is less than 0, which means that the function is decreasing on this interval. And we have one more interval to account for, 1 to infinity, so I'll just choose x equals 2. Seems simple enough. F prime of 2 equals 3 times 2 times 2 minus 1. That's equal to 6. 6 is greater than 0, so it must be increasing on this interval. And just like that, we've basically finished the problem. We've detected our open intervals, and we've classified whether or not it's increasing or decreasing. So maybe we can sketch potentially what the curve looks like. We have critical points at 0 and 1. So, and from -infinity to 0, the function's increasing, so it could go something like this. And then from x equals 0, actually, let me just change the drawing. Let's say, yeah, we reach here. Then from the interval 0 to 1, the function is decreasing. So, whoops. So it could do something like that, right? So I've reached x equals 1. And then from 1 to infinity, it's increasing. So maybe the function looks something like that. Maybe it doesn't, but this function satisfies basically what we've said about the intervals. So yeah, you can actually test it out and see that the function will look something similar to this, like this shape. Just the intercepts might be a little bit different. So yeah, there we go. Pretty fun problem. So now I realized that doing that was a little bit challenging without really figuring out what we're doing. So I developed these steps for finding increasing and decreasing intervals. And this is just explaining what I just did. So f, continuous differentiable function on the open interval. We want to find the intervals in f where f is increasing or decreasing. First step, which is what we did. We found the critical values of f in the interval. We do that by finding the derivative of f, setting it equal to 0 or dne, and solving for x. Next, we write down the intervals. So the intervals, they start from -infinity, and they go to what I wrote, crit sub 1. So crit sub 1 is the smallest critical value. So that's the first interval. Then we go from crit 1 to crit 2, so from the smallest critical value to the second smallest critical value. and so on. If we have n critical values, we go from up to crit n minus 1 to crit n, and then finally our last interval is crit n to infinity. So if we go back to this example, we had two critical values. So we went from negative infinity to 0, then 0 to 1, 1 to infinity. 0 is crit 1, it's the smallest critical value. 1 is crit 2, because it's the second smallest critical value. So we have all of those intervals. Then for each interval, we choose a test value within that interval. It could be anything. Then we take that test value, plug it into f prime of x, to determine the sign. Remember, f prime of x tells us whether or not the function is increasing or decreasing. Because if f prime of that value is decreasing, or is less than 0, then it's decreasing. And if it's greater than 0, then it's increasing. And this is bad notation. It's not f prime of the critical value, it's f prime of the test value. Because we're testing a test point. So yeah, those are the steps written out for you. If you follow these, you'll be golden. So let's move onwards. So now we introduce the first derivative test. So again, we have to go through like what we're assuming that we have. So c is a critical number of a function. F is continuous, differentiable on an interval. The interval contains c. And rather, f is differentiable on the interval, except perhaps not at c. So there's one exception. It might not be differentiable at c. Then we can classify the function evaluated at c as the follows. So if the first derivative changes from negative to positive at c, then there's a relative minimum at c. If it goes from positive to negative, then c is relative max. And if it's positive on both sides of c, or negative on both sides of c, then it's neither a relative min or a relative max. So let's take a look at these pictures. C, it's important to remember c is a critical point. So in this first example here, if we take a look at the first derivative, it's clearly 0 there. The tangent line is horizontal, so that's a critical point. To the left of c, the function is decreasing. The slope of the tangent lines are negative, so it's decreasing. To the right, the tangent lines are increasing. The first derivative is positive. So it goes from negative to positive, which means that c is a relative minimum. If, instead, we go from positive, these tangent lines are all positive, to negative on the right, then c is a relative maximum. So think about it, maximum is like a hill, minimum is like a valley. And here we can see some cases where it's neither a relative min or maximum. So that's when the sign of the tangent lines on both sides are the same. So on the left here, they're all positive. On the right, they're also all positive. So that's neither a minimum or a maximum. This has potential to be something else, which we'll learn about later. And here we see the same thing, negative, negative. So that helps us classify critical points a lot easier. And to do that classification, we're going to introduce the sign line. So it's literally just a line, but we need to learn how to use it. First step is to draw a number line, what I've drawn above. The left side is like the smaller numbers, right side is the larger numbers, just like a normal number line. Next, we find all the critical values of the function, just what we've been doing. Then you want to mark the critical values on the sign line. So for example, this could be like x equals -3, this could be x equals 0, this could be x equals 5, right? It just has to make sense the way that we label it, right? This should not be over here x equals 5 and x equals 0 and x equals -3. That just doesn't follow how numbers work. We want the smaller values on the left and the higher values on the right. So we've marked them. Now, again, we choose test values within each interval. So if we're looking at this interval here, -infinity to -3, I just choose some test value in between. Same thing here. In this interval, I choose something here. This interval, choose something. And then finally, this last interval to infinity, I just choose something. So same, very similar to what we just did with our table. Then we solve for f prime of x using the test values, similar to what we did before. Then you can mark the sign of f prime of x above each interval, and then we can use the first derivative test to draw conclusions. So let's just take a look here. Let's just say this is my test value, x equals -1. Let's just say f prime of -1 is less than 0, or let's just make it greater than 0. Then I would put a plus sign here. So that's saying in this interval, the function is increasing. Now let's just take a look from x equals 0 to x equals 5. Let's just say my test value is x equals 1, and I evaluate f prime of 1 is less than 0. Then I put a minus sign here. So that's saying on this interval, the function is decreasing. Now we can classify x equals 0 using the first derivative test, because at x equals 0, to the left of it, the function is increasing, it's going upwards, and to the right of it, it's going downwards. So by the first derivative test here, that's this case, so we have a relative maximum. So in that case, x equals 0 is a relative maximum. And then we would have to do the interval here, and then the interval there, right? This is just for example. So here we would see that, okay, it's positive to the right, positive to the left, positive to the right. So this is x equals 3 is nothing. And then at x equals 5, it goes negative to positive. So this would be a relative min. So it's very similar to the table that we did previously, except now we have a visual, which I find helpful. So let's just walk through an example with the sign line. We want to find and classify the extrema of f of x equals this function. So the first step is to find the critical points. Take the first derivative, 3x squared minus 12x, factor it out. There's no points where it does not exist, but x equals 0 and x equals 4 makes f prime of x equal to 0. So we take those critical points and mark them on the sign line. Next, we're going to choose test values in each interval. So from -infinity to 0, we just need to choose a value within that interval. So I chose x equals -1. Then we evaluate f prime of -1, we get positive 15. Now we consider this interval, 0 to 4. We test x equals 1 because x equals 1 is within it. F prime of 1 is -9. Lastly, we go from 4 to infinity, and I'm just choosing x equals 5. F prime of 5 equals positive 15. Great. So now we're taking this positive 15, -9, positive 15, and we mark it with the signs, right? This was positive 15, this was -9, this was positive 15, but we only care about the sign of f prime. So yeah, we just mark the signs. Now we use the first derivative test to draw conclusions. Remember, the maxima and minima can only occur at critical points or at the endpoints of an interval. Since we don't have an interval, it's an infinite domain. We don't have to worry about that. We just have to worry about the critical points. So let's start by looking at x equals 0. The function goes from increasing to decreasing. So by the first derivative test, x equals 0 should be a local maximum. At x equals 4, this is a typo, x equals positive 4, the function goes from decreasing to increasing. So by the first derivative test, x equals 4 should be a local minimum. And that's basically the sign line. Yeah. So let's just take a look. I don't think we'll jump into this yet. I think we'll stop here for the day, and we'll continue with concavity and the second derivative test next time. So yeah, we've learned quite a lot today. We've learned how to essentially analyze a function, find its critical points, detect minima, maxima, stuff like that. And now we can analyze where a function is increasing, decreasing, find the critical points, classify them, tons of stuff. Next time, we're going to learn even more things to classify functions with. So that should be quite exciting. So yeah, I think that's going to do it for today. Hopefully this lesson was educational. And yeah, so tomorrow, Thursday, Physics C content, and then we'll be back next week, Monday, Physics, Wednesday, Calculus, and then Thursday, Physics C. So yeah, thank you for watching, and until next time, take care.